obligatory Star Trek takeoff introduction. To boldly go where no one has gone before. Chevy Chase, Maryland.
Magnetic fields exert force on things that are magnetized, like compass needles. Magnetic fields also exert force on moving charged particles, like ions.
Magnetic fields have direction. The fields point from north poles to south poles. What does that mean?
Think about the last time you played with refrigerator magnets. Some sides stuck together and others wouldn't, right? That's because of the north and south poles of the magnets, and the magnetic fields the magnets create.
Here are the magnets. They have north and south poles. The poles are concentrated areas of magnetic field.
So that still doesn't really tell you how magnetic force works. Basically, we find that opposite magnetic poles attract, while similar poles repel. Moving charged particles are deflected by magnetic fields.
We can draw lines like this to show the direction of the refrigerator magnet's magnetic field. See, the field points from the north poles of the magnets to the south poles. If you stick the magnets together, touching the north and the south poles together, everything's fine, because the magnetic field still points from north to south. But if you try to stick the north pole to the north pole, the magnets won't stick. The magnetic forces are pushing against each other and won't let the magnets stick.
When we draw a picture of a magnet and a magnetic field, the lines that we draw showing the direction of the field are called field lines.
So by now, I bet you're wondering, the Earth has a magnetic field. Where did that come from? Well, this is where everything comes back together again.
The inner and outer cores of the Earth are made of conductive metals. The inner and outer cores spin at different speeds. If you remember from a few minutes ago, we said that when a conductive metal is inside another conductive metal and they spin at different speeds, electricity and a magnetic field are created. So, that's exactly what's happening at the core of the Earth. The solid inner core and the liquid outer core spin at different speeds and create electricity and magnetism. The electricity doesn't affect us much. It just keeps to itself down in the core. But boy, does the magnetism affect us.
On Earth, we use the magnetic field to help us get around. We make compasses by suspending a small magnet in some water. The north and south poles of the magnet align with the north and south poles of the Earth's magnetic field. We put a little arrow on the part of the magnet that points north, and from then on, we always know which way is north.
Remember when we told you about ions? Ions are those little charged particles that just scoot around in space sometimes. We call them cosmic rays. Because cosmic rays have positive and negative charges, they are deflected by the Earth's magnetic field. A few zip through and hit the Earth's atmosphere. The slower-moving cosmic rays spiral around the Earth's magnetic field, which sends them on a tighter and tighter spiral towards the north or south pole of the Earth. Many of these spiral right back out away from the poles. This is good, because otherwise we'd get cooked by all that extra radiation.
So, let's talk about something specific about the Earth's magnetic field that's weird. But before we do, we need to understand something about magnetic fields.
When two conductive metals spin and create a magnetic field, like we described above, the magnetic field's north and south poles are created perpendicular to the spin of the metals.
Much earlier in the tape, we told you about the Earth's north and south poles, which mark the axis on which the Earth revolves. The Earth spins on its poles.
Well, the inner core and the outer core don't spin around the same axis that the rest of the Earth does. The core spins in a completely different plane. That means when the inner and outer cores spin and create a magnetic field, the magnetic poles they create are in a different place than the north and south poles of the Earth.
That generally doesn't cause much of a problem, but you should know that they are in different places.
The other important thing you need to know about poles is that every few 100,000 years or so, they flip. North becomes south, south becomes north.
They're not entirely stable.
Nice place you got here.
I like you.
Thank you.
That's enough about the magnetic field. Let's go back to the Earth.
Can we have nachos first?
Yeah. Yes.
And now, the atmosphere.
Section B, the atmosphere.
Above and around us is the atmosphere, the big sea of air in which we live.
The atmosphere has a couple different layers: the troposphere, the stratosphere, and the ionosphere. We live in the troposphere.
The troposphere stretches from the ground to about 15 kilometers above the surface. This is the area of the atmosphere where convection occurs.
Stand by for an explanation of convection. Over.
Convection is caused by the heat of the planet's surface. You probably already know that warm air rises and cold air sinks. As air flows over the Earth, the warm surface of the Earth heats the air, causing it to expand and rise. When the air rises, it cools and sinks back down again. This cycling of hot and cold air is convection. Convection causes surface winds and weather.
Above the troposphere is the stratosphere. The stratosphere is where the ozone layer hangs out. Ozone is a different flavor of oxygen than we're used to. We breathe O2, which is 2 little oxygen atoms stuck together. Ozone is O3, 3 oxygen atoms stuck together. The ozone layer, as long as it lasts, protects us from harmful ultraviolet radiation. Above the stratosphere is the ionosphere, where all kinds of ions drift around. These ions are produced when cosmic rays and other radiation hit the upper atmosphere.
The ions in the ionosphere reflect some radio waves. That's why sometimes late at night you can pick up radio stations from Louisville and other faraway exotic locales. The ionosphere doesn't stop TV waves, however, so that means we're blasting I Love Lucy reruns into space.
Ions and electrons can also be found trapped in the Earth's magnetic field further up, outside the atmosphere, in a region called the Van Allen belts. Ions created by the solar wind shoot toward Earth, and because they're charged particles, they get deflected by the magnetic field. Some of the ions are deflected enough that they get trapped in the magnetic field in the Van Allen belts. The ions continue to spiral around the magnetic field and eventually make their way to the poles, where they collide with the Earth's atmosphere. Those collisions make the big, colorful light displays we call aurora.
You may have seen aurorae before. They're sometimes called the aurora borealis, or the northern lights.
Section C, the turning Earth.
So we all know the Earth revolves, right? Well, how do we prove it?
An easy way is to use a thing called a Foucault's pendulum.
Imagine going to the North Pole and setting up a frame like this. From the middle of the frame, directly above the pole, we hang a pendulum. Now we start the pendulum swinging and mark the place on the ground that the pendulum swings over. And then we look at the sky to see what star the pendulum is swinging towards. If we leave and come back in 3 hours, the pendulum isn't swinging over the same spot that we marked on the ground. But if we look at the sky, we see that the pendulum is still swinging toward the same star. The simplest and therefore the best explanation is that the Earth moved under the pendulum.
These big pendulums are called Foucault's pendulums. They're named after the guy who had the idea to make them.
Foucault's pendulums work anywhere on the Earth, but there's some really complicated trigonometry involved in explaining why they work all around the Earth. So we're not going to explain that. Just remember that Foucault's pendulums are proof of the rotation of the Earth.
Another proof of the Earth's rotation is this thing called the Coriolis effect. The Coriolis effect is the swirling of fluids like air and water that is caused by the rotation of the Earth. Sound complicated? It is.
Here, watch this planet. See how it turns? Okay, the circumference here at the equator is pretty big, and the circumference here up by Greenland is pretty small, but they rotate once around in the same exact amount of time. So, land by the equator is actually moving faster than Greenland.
Did you catch that? Qaqortoq, a town in Greenland, is up here. And if we look straight down below Qaqortoq to see what's on the equator, we find a little town in Brazil called Belém. Both Qaqortoq and Belém rotate once around the Earth every 24 hours. But Belém has farther to go, because the Earth is bigger around at the equator than it is up by Qaqortoq. So the land at the equator is actually moving faster than the land by Greenland.
Imagine you're at the equator in the suburbs of Belém. You fire a cannon due north toward Qaqortoq. As far as you can tell, the cannonball goes straight. But does it really?
To figure this out, we need to remember some physics. You fire the cannonball with a certain velocity due north toward the pole. But remember that you are also already moving east pretty fast. Because at the equator, you're moving really fast because of the rotation of the Earth. So the cannonball is moving north because you fired it that way. But looking from space, it's also moving east because you and the cannon were moving east when you fired it. Now remember, the higher latitudes are not moving as fast to the east as the equator because they don't have as far to go. But the cannonball keeps its initial eastward motion as it moves north. So the ground to the north won't be moving as fast eastward as the ball. From the ground, the ball is seen to start going north, but then curves toward the east as it travels north.
This curving toward the right works for any object moving over the northern hemisphere, air, water, clouds, whatever. In the southern hemisphere, the curve is in the opposite direction, to the left.
The Coriolis effect can explain how hurricanes and tornadoes spin. Hurricanes and tornadoes are low-pressure centers, which means that the air around them is moving in toward them. The right turning curl as the air moves in forms the swirl of the hurricane or tornado. If you're caught in a tornado that's spinning counterclockwise, you know you're in the northern hemisphere.
Section D. Other things to know about the Earth.
There are a few more things you should know about the Earth. Let's run through them.
The Earth's distance from the Sun is 1 AU. If you remember, an AU is the length of the semi-major axis of the Earth's orbit. 1 AU is equal to about 150 million kilometers.
The Earth's revolution period is 1 Earth year, or 365.25 days. A revolution period, if you remember, is how long it takes a planet to orbit the Sun.
The average density of the Earth is 5.5 grams per cubic centimeter. The density of water is 1 gram per cubic centimeter. So the Earth is a lot denser than water, more like rocks and metal. 5.5 is about the density of your average rock, so we might figure the Earth is mostly made of rock.
The circular velocity of the Earth is 8 kilometers per second. An object circling the Earth has to have a velocity of 8 kilometers per second to stay in orbit around the Earth, just above the Earth's surface. The escape velocity of the Earth is 11 kilometers per second. To escape the gravitational pull of the Earth, you need to be moving 11 kilometers per second. Once you're moving that fast, you've left the Earth's orbit and you're on your way to, well, somewhere else. Just so you know how fast that really is, it's about 40,000 kilometers per hour.
How many miles per hour is that?
The escape velocity in miles per hour is about 25,000 miles per hour.
The pressure of the Earth's atmosphere at sea level is equal to 1 bar. A bar is a measurement of air pressure equal to about 15 pounds per square inch. The pressure of the atmosphere comes from the weight of all that air in the atmosphere pressing down on the surface of the Earth. The higher up you go in the atmosphere, the less air there is, and therefore the less pressure.
The Earth's atmosphere is composed of 78% nitrogen, 21% oxygen, and 1% other stuff.
That's enough about the Earth. Let's move on to the other thing that hangs around with us, Luna, the moon.
Part 7, the moon.
Section A. Origin of the moon.
Where did the moon come from?
The best guess right now is that soon after the Earth was formed, when it was still liquidy, something really big pounded into the Earth and knocked a big piece of the mantle into space. The big, glooby chunk solidified and became the moon. Scientists call this theory
the Great Impact Hypothesis.
We'd also like to share one of our favorite theories for the origin of the moon.
The moon is actually a giant research station that was erected by an alien civilization about 10,000 years ago. From the moon, the aliens have a convenient base for studying the development of our civilization and species.
Section B, surface features of the moon.
Two landscapes dominate the surface of the moon, the Maria and the highlands.
The Maria are plains covered with dry lava. It's been that way for at least 3 billion years. There are no active volcanoes on the moon anymore. The moon is geologically dead.
The highlands are the older parts of the moon. We know this because the highlands have more craters. How does that work? Well, we know that craters on planets and moons are made by collisions with debris flying around the solar system, and that these collisions have been going on since the solar system was formed. This means areas of the moon with more craters are older, right? They've had more time to get cratered.
Where did the crater-making debris come from?
In space, there is some random junk that just flies around, like rocks. We call the junk meteoroids. There are also comets zooming around and a good deal of dust. When these rocks hit the Earth or moon, they can be moving really fast, up to 30,000 miles an hour. Rocks moving that fast can cause a lot of damage. So when they hit the moon, boom, crater is formed.
The surface of the moon is covered with a powdery soil called regolith. There are two reasons why the moon is powdery.
The first reason is that the moon is constantly bombarded by lots of small stuff from space. The Earth is too, but when things hit the Earth, friction with the atmosphere causes them to burn up and go away. The moon doesn't have an atmosphere, so all of the meteoroids and things that head toward it don't get burned up before hitting the surface. That means an awful lot of things hit the moon that wouldn't hit the Earth. Either way, all of this pounding makes for a lot of powdery debris.
The other reason the moon is powdery is a phenomenon called thermal shocks.
We all know that things expand when they're hot and shrink when they're cold, right? That's why they make sidewalks with cracks already in it.
Because the moon doesn't come with cracks already in it, because the moon doesn't have an atmosphere, there's no insulation to smooth out the daily changes in temperature. The moon goes from really hot to really cold very quickly. The quick change in temperature causes the rocks of the moon to expand and contract very quickly, which puts a lot of stress on the lunar rocks. The stress makes the rocks break apart. They literally crumble into dust.
So scratch this on your head. The surface of the moon is powdery because of bombardment by space stuff and thermal shocks. The powder is called regolith.
Oh yeah, by the way, the lack of atmosphere on the moon also means it has no weather. No wind, no rain, no nothing. So, as well as being geologically dead, the moon is also meteorologically dead.
Section C, phases and rotation of the moon.
Pink Floyd called their album The Dark Side of the Moon. Unfortunately, astronomically speaking, there is no dark side of the moon. There is, however, a dark side of the Force.
Instead of a dark side, the moon has a far side.
This is because of the force of the Earth's gravity. Long ago, the gravity of the Earth distorted the moon, making it lopsided. The Earth's gravity continues to pull on the bulge, making that side always point toward the Earth. And so, the same side of the moon is always facing the Earth. So when we look at the moon, we're always seeing the same side.
The moon takes about 27 1/3 days to go around the Earth, but the moon goes through its lunar phases in 29 1/2 days. The reason for this is a bit complicated. For now, just remember that the moon's cycle of phases lasts 29 1/2 days. It'll come in handy later on.
If you're still kind of shady on how that works, check this out. This guy's the Earth, and the soda can is the moon. His arm is the force of gravity. You, my viewing friends, are the sun. As the moon goes around him, it makes one rotation on its axis, and you get to see every part of it once. Make more sense now?
The same side of the moon is always facing the Earth, but every part of the moon faces the sun at one point or another during that 29-day cycle. That's why we can't see the moon sometimes. We see the moon when the side of the moon that's facing us has sunlight shining on it. If the far side of the moon, the part we never see, is facing the sun, our side is in shadow, and we can't see it.
How much of the moon we see is determined by the angle between the Earth, the moon, and the sun. If the moon is between us and the sun, for example, we don't see the moon at all, because the part of the moon that is lit by the sun is facing away from us.
Actually, if we really tried, we could see the moon, because enough sunlight reflects off of the Earth to light up part of the moon that's in shadow. But as far as we're concerned, you can't see it.
If the Earth is between the sun and the moon, we see a full moon, because the whole side that's facing us is lit up by the sun.
Doesn't the Earth get in the way of the sunlight?
Sometimes, but not often. The moon orbits the Earth at an angle, so the Earth doesn't get in the way much. A phase of the moon is what the moon looks like to us during a certain period of time. It's how much and which side is lit up.
So now we're going to show you all the phases of the moon in order, from new moon, when we can't see it, all the way through full moon and back to new moon again. One cycle through all the phases is the 29.5-day lunar cycle. Each phase lasts about 4 days.
New moon. You need a new moon in this phase, because you ain't got one. Waxing crescent. If you see more of the moon on the side facing west, it's waxing. You can remember what a crescent moon looks like because it looks like a crescent roll. First quarter. Here's how you remember this one. A quarter is a half. Sounds stupid, but it works. A quarter is a half. This is called the first quarter because the moon is 1/4 of the way through its cycle. Waxing gibbous. Gibbous is a funny word, and that makes sense because this is the phase when the moon is the most funny looking. Full. This one's pretty obvious. Now for the waning stages. You see more of the moon on the side facing east. Waning gibbous. Funny moon, funny name. Third quarter. A quarter is a half. Since it's the east half of the moon, it's the third quarter. Doesn't make any sense to me either, but that's how it works. Waning crescent. Moon crescent roll on the left side. New.
Let's run through those once more.
New, waxing crescent, first quarter, waxing gibbous, full, waning gibbous, third quarter, waning crescent, new.
Got that?
Oh yeah, baby.
The moon doesn't just spin around the Earth and show us its pretty phases. It has an effect on what happens here on Earth.
Section D. Tides.
The moon orbits the Earth because of the Earth's gravitational pull. But the moon is big enough to have plenty of gravity of its own. In fact, the moon has enough gravity to affect the Earth.
Tides. The gravity of the moon pulls on all sorts of stuff on the Earth. Stuff that's closer to the moon gets pulled harder. Stuff that's further away gets pulled less hard. The water on Earth can move easily by this pull, and that's where we witness the effects of tidal forces.
The water closest to the moon gets pulled toward it, making a bulge, and the water on the sides gets pulled over toward the moon. And this water over here, on the far side from the moon, isn't close enough to the moon to be as affected as all the rest of the water, so it just stays where it is, thank you. This gives us 2 tidal bulges, one on the side of the Earth closest to the moon, and one on the opposite side.
The sun has a similar but smaller effect on the oceans and tides. When the sun and moon get together to pull at the oceans, oh, whoa, look out.
By the way, when the sun, moon, and Earth are all in line, it's called syzygy, and eclipses sometimes happen.
Whenever the Earth, moon, and sun are all lined up, if things work out just right, the Earth and moon can cast shadows on each other. These events are eclipses. If the Earth casts a shadow on the moon, that's a lunar eclipse. If the moon casts a shadow on the Earth, that's a solar eclipse.